Hello, this video will be discussing about sets, terminologies, and its applications. First, we have the terminologies. So first, we define sets to be an unordered collection of elements which are denoted by uppercase letters. And it can be described via three different methods. First, we have the roster method, which lists down all the elements in the set. Then we have the set builder notation, which actually is a shortcut to define what kind of elements you have in the set, especially for integers or any number in general. And lastly, we also have the Venn diagram, which can be used to visually describe the elements in a set. So here in this Venn diagram, we have elements in set A in the left, and in the right, we have set B elements. Both sets are encompassed by the universal set, which contains elements of set A, set B, and other elements that are not in both sets. So here we have two symbols that are used often. First, we have something to denote that an element is in the set, and something to denote that an element is not in the set. So how do we use this? So here we have given set F, which contains different kinds of food over here. So to say that something is an element of the set, we need to use, again, this symbol. And as you can see here, the buko here is part of set F alongside the grapes, bananas, and apples. And because of that, that would mean that they belong into the set, and so you would have to use this symbol over here. Now, if something is not in the set, then you would have to use this symbol. As such, you use it for items like the orange, chocolate, bread, and peaches, which are not in the set F. So next, we have infinite sets, or sets that cannot be counted by us. So here we have the set of all real numbers, which contains irrational numbers, rational numbers, integers, and the likes. And here we have natural numbers, which actually can start with 0 or can actually start with 1, depending on the context of the problem. For this slide, we will pertain to natural numbers as starting with 0. Then, we also have real numbers, or positive real numbers to be more specific. And here is where we use the set builder notation. So here, we say that the positive real numbers can be defined as element n, where n is a real number, and n is greater than 0, or n is positive. So if a number fulfills these two conditions, then it is part of the set. So there are other more sets to be discussed here. We have the set of all integers, negative, positive, and 0. Then we also have rational numbers, which is a ratio based from the word rational, which is a ratio of two integers where q, or the denominator, is not equal to 0. Then we can also use an abbreviation or accent for to define negative integers using the negative sign, and you can use it to define negative integers, or maybe even negative rational numbers or negative real numbers. But for this one, it shows negative integers. So here we have even more symbols. Here is the symbol used to define equal sets when two sets have the same elements. This is formally defined as is for all elements x. X is in A if and only if x is in B. So given sets F and G, are they considered to be equal? So given set F over here and set G over here, we need to show that for all of X, X is in A and X is in B. Okay. So to determine as so, we first look at set F. Since the apple is in set F, we need to also look for it in set G. And because it's here, then we're not yet done to determine whether they are equal or not. So you need to continue to do this to the other elements. So the siopaw is also in both sets, the banana is in both sets, as well as the pear. And because of this, we can say that set F is equal to set G. So let's proceed to another example. Here we have the same items from the previous item. However, we have the grapes here in set F. Let's say, let's do it here. So we know that the grapes, let's represent it as X, is in set F. However, X is not in set G. Therefore, this would make the biconditional statement false. And because you have a for all, remember, if you have a for all universal quantifier rather in your statement, then that would mean that one statement that is false would make the entire thing false. So therefore, F is not equal to set G. Here's another item. This is also not equal because the grapes is not in set G and the chocolate is not in set F. So therefore, like the previous item, these sets are not equal. So what about this one? We have this time duplicate items in the same set. Would this still be considered equal? Well, just by looking at the definition, we are to show that if X is in A, then it should also exist in B and vice versa. So the apple is in here, which is also in here, and this apple can also represent is also present in this other set, and this apple is also present in set G, and so on and so forth. As well as the bananas, they are also present in both sets. The pears are also present in both sets, as well as the siopaw. They are also present in both sets. So even if there are duplicate items on both sets or in either one of the sets, this would still make the both sets equal. So therefore, set F and set G are equal for this case. So here we have even more symbols to discuss. Here is the null set, which is a set with 0 elements. Another way to describe it is to basically have curly brackets with nothing inside it. So we can think of empty sets as empty boxes. So here, let's show different kinds of cases. So here we have a box containing 1 and 2, which we can represent as a set containing 1 and 2. Then here we have the null set, which contains, by its definition, nothing. So therefore, it's null. Next, we have to take note also that sets can be elements of another set. So in this item, here we have a set containing a set which is null. So a set containing a null set. So the question is, before that, it's also a box inside a larger box. So is the purple box empty? No, because we actually have a null set, which is represented by this one over here. It is an element in the purple box, which means it's not empty. It contains something, and that something is empty. And then lastly, we have an a set containing the null set and a set containing 1. So there are two items in the purple box, which is an empty red box and a box containing 1. So here are the four cases that we just discussed a while ago. And take note, the null set, and this is very important because it can get confusing if you study sets for the first time. The null set is not equal to the set containing the null set. These are completely different. Think of it this way again as a set containing nothing and a set containing something, which is this null set over here. So take note. Then we also have a singleton set, which is a set with one element. An example of this would be this set over here because it contains one element, and that element is the null set or the red box. So now we'll proceed to other definitions. Here we have A is a subset of B, where all elements of a set or set A are elements of a larger set B. So this is formally defined as so for all of X, if X is in A, then that implies X is also in B. So here we have an example given sets T and S, where T contains the animals bear, rabbit, squirrel, fox, and penguin. And set S contains penguin and a squirrel. So we need to show that S is a subset of T. So looking back at the definition again, it says that if X is in A, then X is in B. And what we're looking for is if X is in S, then that means X is also in T for all elements X. So first we have the penguin over here, which is part of set S and is also part of set T. And then the next one is we also have the squirrel, which is also present in set S. Additionally, it's also present in set T. And because both are present in set S and set T, then we can form a subset from S with respect to T. So therefore, S is a subset of T. Take note also that the null set is a subset of the set S, and a set is a subset of itself. So here, we can also say T is a subset of itself, and the null set is a subset of itself. When we say that T is a subset of T, then that just means that for all of X, if X is in T, then X is in T. Which, just by looking at it, would be true because if an element is in a set, then you'd also still be in that same set. So therefore, if you take into account all the elements of set T, for example, and then you apply it to this statement over here, it would become true. Therefore, the set is a subset of itself. And then another case is if the null set is a subset of the set. So for all of X, we can translate this into if X is an element of the null set, then X is an element of the set. Notice how this one would always be false, because it cannot be possible that an element is part of the null set, which contains nothing to begin with. And for implication statements, remember, if the premise is false, your consequent, regardless of its value, whether it's true or false, it would just be equal to true. So therefore, this statement that the null set is a subset of the set T or any set is true. So now we have the proper subset, where all elements of a set are elements of a larger set, and there exists an element in the larger set that is not in the other set, formally defined by here. So this definition, this first part of the definition, is something you already know. This means that A is a subset of B, and there exists an element X where X is in B, which is not in A. So let's look at the same example from a while ago and show that S is also a proper subset of the set E. So here we replace the definition a while ago with our sets to make it easier to understand. And we already solved that S is a subset of T from a while ago. So we don't need to worry too much about that. We need to focus on the other half of the definition, which in X is an element of T, which is not in S. And there are actually three possible answers to elements that are in T, which are not in S, such as that of the bear, the bunny, and the fox. All three are not in S. Therefore, we can say that S is a proper subset of T, because not only is S a subset of T, there exist elements, at least more than one, no, at least one rather, where X is in T, which is not in S, which are shown by one of the three possible answers over here, or elements. Take note that the null set is a proper subset of a set, but a set S is not a proper subset of itself. So next we have the cardinality of a set, which is the number of distinct, emphasis on distinct elements in the finite set. So here we have a set A containing numbers 1, 2, and 3. And since we're looking for the cardinality, the answer would be 3, because there are 3 distinct elements. So what if there are duplicate values now? Well, because we're still looking for distinct elements, we need to find what are the distinct elements of the set. So we have 1, 2, and 3. The other duplicate 2 and the other duplicate 3s will not be counted in the cardinality of the set. Therefore, the cardinality of the set would be 3. Take note also that the empty set or null set is equal to 0. Although this is not discussed in CCDSTRU, this is something that you may want to think about. What about the cardinality of infinite sets? And are they equal with each other? So here we now have the power set of a set, which is a set containing all subsets of a set. Basically, a set with n elements will contain a power set with 2 raised to the n elements. So here we have the set B, which contains the elements 1 and 2. First, we need to find the cardinality of the power set. So again, a power set contains 2 raised to the n elements, given that the cardinality of S is n. So here we have set B whose cardinality would be 2. Therefore, the cardinality of the power set of B would be 2 raised to 2, which is 4, which is stated over here. And then we now list down the list of elements in the uh, power set. So from a while ago, in our discussion on subsets, we know two things. A null set is a subset of a set, and a set is a subset of itself. So by that, we already have two elements that we know that can be part of the said power set, one containing the null set, and then one containing elements the actual set itself, 1, 2. We need to also consider that since we need 4 elements, we need to think of other subsets of B, which will be part of the power set. And that would be individually 1, and the other singleton set 2. 1 is a subset of 1, 2, because based on our definition, if X is in A, that implies that X is in B. And because 1 is in this set A, for example, then it's also present in set B, which has the 1 over here. Actually, no, this is wrong. We're pertaining to this. Actually, no, that's wrong. Also, we're referring to sets. So here, since X contains 1, or the other way around, 1 is in the element, 1 is in the set A, then that implies that this element 1 is also in the set B, which is here. As well as if we replace 1 with the other element 2, 2 is in the set A, then that also means that it's also in the set B, which is this one. So with that, this would be your power set already. So again, it would contain the null set, the singleton sets 1 and 2, and the actual set B 1, 2. And that's it. Now, what if you have 3 elements? Again, for finding the power set's cardinality, then that would mean you have 2 raised to n elements, which is 2 raised to 3 because C has a cardinality of 3. So therefore, it would have 8 elements. And the list of elements in the power set are as follows. The null set, the singleton sets 1, 2, and 3. And then we also have other sets like the set containing 1 and 2, 2 and 3, and 1 and 3. And then as well as set C itself containing elements 1, 2, 3. So as we grow to have even larger power sets, how can we easily find them? Or is there a strategy or algorithm to follow to get the elements of a power set? We can construct a truth table to actually get all the elements of a power set. So let's look back at the previous example. We first create n columns and 2 rows. So that would pertain to these columns and then have 8 rows, which is 2 raised to 3. Fill up the table with true and false as how you did it with propositional logic in CCDSTRU, formatting it properly so that you don't get confused on finding for the subsets later on. So those that are true are elements that belong in the subset. So what do I mean by that? Notice how here 1, 2, and 3 are true. Therefore, the subset would contain 1, 2, and 3. In the next subset, we have 1 and 2 only, which are true, then 3 is false. So we will just include 1 and 2. So, and then we have something like this, where 2 is the only one that is true, and then 1 and 3 are false. Then 2 would be the only one in the subset. And if all 3 are false, then all 3 are elements are not in subset, which means it's just the null set. So here, each subset is an element of a power set or of the power set. So next we have tuples. Here we have an ordered n tuple which contains n elements, which is an ordered collection as compared to sets. An ordered 2 tuple is an ordered pair A, B, which you've seen a lot in plotting graphs. So like if we have 1, 1 here, that's an ordered pair. Or if we say we have something like x negative y, then this is also another ordered pair. So here is the definition of a Cartesian product, which is a set of all ordered pairs where A is in this set A and the element B is in the set B. Formally defined by the ordered pair AB, where A, the element, is in set A and the element B is in set B. So here we have an example of the Cartesian product of set 1, 2, 3 with set 4, 5. So how do we actually compute for the elements in the Cartesian product? Place the first set as the rows part of the tuple. Place the second set as the columns part of the tuple. And then fill up the table like so. The first element will be placed in the ordered pair first before the second set's element, since that's how we defined it in the Cartesian product. And then fill up the remaining cells like so, where each cell is an element of the Cartesian product. So if we did it the other way around, like let's say 4, 5 by 1, 2, 3. First, you need to set up the rows, which are 4 and 5. These are your, since that's the first element. Then we also have 1, 2, 3. And then fill the table like so. So this would contain this time element 4, 1, or ordered pair for one another. Then 4, 2, 4, 3. Then 5, 1, 5, 2, 5, 3. So that would be the Cartesian product's elements for this Cartesian product. So also take note that ordered pairs are not necessarily commutative, since the order here matters. Like if we have, let's say this is 1 and this is 2. 1, 2 would be here. And then 2, 1 would be over here. And notice that they're not referring to the same point. Therefore, they are different in terms of values. So what if we have more than 2 Cartesian products? We have a Cartesian product of 10 sets. This time, it's a set of ordered n tuples, which contains n elements, where we formally define it as the ordered n tuple, such that a sub I is part of the set a sub I for I equals 1, 2 until n. So how do we do this time? Let's say I have 1, 2, Cartesian product of 3, 4, Cartesian product of 5, 6. Now, the table method that I showed a while ago would not work because this time it has 3 sets. So how do we do it like so? First, we look at the first element of the first set, which is 1. Then, look at the first element of the second set, 3. And then the third element of the first set, 5. So that would be your first element. Then, look at the first element of the first set, first element of the second set, and then second element of the third set. Because we're done with 5, we will now use 6 here. And then, go back from 1 again. And then, since we're done with 3 in the second set, we can now proceed to 4. And then start from 5 again. And then continue on with 6. And then since both elements in set 2 are exhausted, we're done with the element 1 over here. Then we can proceed with the element 2. Then start over again. So 2, then first element, second element, first element, second element, followed by first element, second element, first element. So that's 2, 4, 5. And then the last element is 2, 4, and 6. And that would be all the items in the Cartesian product. You can also think of it as for loops in programming. For, let's say, A sub I in capital A sub I. No. Let's do it this way. For A sub 1 in A sub 1. For A sub 2 in A sub 2. For A sub 3 in A sub 3. Print the tuple containing A sub 1, A sub 2, A sub 3. There. So think of it this way in computing for the Cartesian product of n sets as a nested for loops, where if you have n sets, then you will have n for loops. So that is one way to visualize how you can get the Cartesian product of more than 2 sets. So here are some exercises that you can use. So here are the items, which are just true or false. You can pause the video here. And the next slide would be the answers. So now, we'll proceed with the set operations. So here we have the union of 2 sets, which is a set containing elements either in A, B, or both. Formally defined by, like so, X such that X is in A or X is in B. So given sets A and B, where A is the set containing the numbers from 1 to 5, and B is the set containing the numbers from 4 to 8. So let's say this is 1, 2, 3, 4, 5. And then we have 4, 5, 6, 7, 8 for set B. This one's set A. So if you want to get the union of both sets, we apply the operation like so, and you would result to a set containing elements that are either in A or in B. So this one, A union B, would be equal to 1, 2, 3, 4, 5, 6, 7, 8. Take note that I did not include the duplicate 4 and 5 in the union set. So the next item would be, let's erase this first, the intersection of two sets, which is a set containing elements that are in A and B. So with that, it means that it's an element X such that X is in A and X is in the set B. So looking back at the items that we have a while ago, if you want to get the intersection, you look at elements that are both present in A and in B. And in this case, we would have elements 4 and 5 in the intersection of the set, which would be shown right here. So with this, we see that the intersection of A and B would contain the elements 4 and 5. So let's proceed to the next item. So if A intersection B is disjoint, results to a null value rather, then A and B are disjoint. So what would disjoint sets look like? It would look something like this, where the sets don't intersect at all or don't have a common value for them to intersect. So this would be an example of a disjoint set because when you intersect them, it's just the empty set or the null set. So next is the difference of two sets, which is the set containing elements that are in A but not in B. As we, the formal definition for this is an element that is in A but is not in B. And if we want to look for the other way around, for B minus A, then we can say it is X such that X is in B and X is not in A. And that would be for B minus A. So how do we visualize this? Let's say we have the same items from a while ago. 1, 2, 3, set A, 4, 5, 6, 7, 8 for set 4, 5, 6, 7, 8 for set B. So if you want to look for the difference, you take away elements. If you're looking for A minus B, we take the elements that are in A, which are not in B. So we are taking elements that are in A, which are also not part of B. 4 and 5 are in A, but they're also part of B, so they won't be included in the set. 6, 7, 8 are part of B, so they won't be part of the difference of A and B. So the answer should be 1, 2, 3, which would be shown over here. You're sort of cutting out the set B based on the given sets. If you want to look for the other way around, you're cutting away the set A from set B. So that would result to 6, 7, 8 if you are looking for the other difference, which is B minus A. So now we have to look for the complement of a set, which is the set containing elements that are not in A. So basically, it's also the difference of the universal set and another set, which is formally defined by X being part of the universal set, where X is not part of A itself. So if we say that this is set A, then the complement of the set would basically be any elements that are not in A but are part of the universal set. So look at the difference between set A and its complement. So let's say our set universal set is the numbers containing 1 to 100. Our set A contains, let's say, 5, 6, 7, or 5 and 6, rather. The complement of that set, considering that A is part of the universal set, would be numbers 1, 2, 3, 4. Then we skip 5 and 6 because they're part of A. So we move on to 7, 8, and then so on until 100. And that is an example of the complement of a set. So here are some exercises for set operations. Here are the items. You are to determine whether they are true or false. And the next slide, it will contain the answers for the exercises. You may pause the video to look at the items and the answers. So before proceeding to the principle of inclusion-exclusion, there is something that I forgot to discuss, which are set identities. So with set identities, these are somewhat similar to your rules of logical equivalence in propositional logic. However, they are actually quite the same in terms of rules, so you don't have to worry about memorizing them all over again. The key differences are that the end is somewhat the same as the intersection. Your or is somewhat the same as your union. And your negation is somewhat similar to the complement of a set. So if you have something like De Morgan's law, for propositional logic, you define it something like this, where you distribute the negation over the operations and operands where the and comes or and vice versa, and you'll get something like this. Similarly, for sets, if you are to take the complement of, let's say, the intersection of two sets, this is equivalent to the complement of A union the complement of B. And you can factor out also the complement like how you would in negations. Somewhat similar rules that follow also are commutative, associative, involution, identity, domination, idempotent, distributive. One, two, three, four, five, six, seven, 8. So these are some of the rules that also apply in sets compared to when you compare to the propositional logic rules of logical equivalence. Another thing to take note, since identity and domination require true or false values, your true would be, in this case, the universal set, and your false would be the null set. So you may see for yourself to visualize it using Venn diagrams to actually show that these also hold for the following rules as well. So now we proceed with the principle of inclusion-exclusion, which basically finds the number of elements in the union of n finite sets. So basically, you're looking for the distinct elements for each possible set in the union of n finite sets. So for example, we have set A and set B. assuming they are not disjunct. So if you want to look for the elements of, let's say, let's first define our elements A, like the one from the previous items a while ago. So you have 1, 2, 3, 4, 5, then 4, 5, 6, 7, 8. So we want to count how many elements are in the union of the sets. So if we count it like so, we would have 1, 2, 3, 4, 5. So there are 5 elements in A. Then there are 1, 2, 3, 4, 5 elements in B. So therefore, the union would be 10 elements, right? Wrong. Because notice that we counted 4 and 5 twice. And that is what the principal inclusion-exclusion wants to avoid. Double counting elements in the union of n finite sets. So how do we actually compute for the number of elements for the union of two sets? So we first get the cardinality of A, that would be 5, plus cardinality of B, which is also 5, minus their intersection, which would be 2. This one, the subtraction of A union B, its cardinality, is crucial to remove the duplicate counting in counting the number of items in the set or in the union of the sets. So this would be the case for 2 sets. There are also other cases for more than 1 set, more than 2 sets, which are 3 sets and above. So this is the general formula for the principle of inclusion-exclusion, which you do not have to memorize because it looks pretty complicated to explain and derive the said formula. So let's simplify that further with an example. So there are 345 students at a college who have taken a course in calculus, 212 who have taken a course in discrete mathematics, and 188 who have taken courses in both calculus and discrete mathematics. How many students have taken a course in either calculus or discrete mathematics? So let's first define our sets. This one would be for calculus, this one would be for discrete mathematics. So this one is for calculus, this one's for discrete math. Okay, so we have 345 who have taken calculus, 212 who have taken discrete math, and 188 who have taken both. So we're looking for those that have taken either calculus or discrete math, which would imply the total number of students, regardless if they took calculus only, discrete math only, or both. Okay, so first, what we can do is actually start from the more specific sets, going to the more general sets. So what do I mean by that? We first focus on this one. The 188 students that took both calculus and discrete math can actually fall under it. And from there, we can actually derive how many have taken calculus but not discrete math, and vice versa. So here it says also that 345 have taken calculus, which means that it doesn't necessarily imply that those that only took calculus are 345 students. This actually means those that are taking also discrete math, which are also part of the 345. So in this 345, it consists of those that took calculus only, or those that took calculus plus discrete math. So to get those that are only taking calculus only, because we are already done with this one, we can simply subtract 188 from 345. And with that, you can simply find for the value like so of the number of students that took calculus only, which in this case would be 157. So if you sum them together, that would equal the number of students that took calculus, may it be by itself or with discrete math. Similarly, if you want to take the number of people that took discrete math only, subtract 188 from 212. So this would be 188. So that would be 24. Let's make sure, double check. Okay, so it is 24 students that took discrete math only. However, we're still not done because we're looking for the number of students, the total number of students that took either calculus or discrete math. And with that, you simply just add them together. So 157 plus 188 plus 24 should result you to 269 students all in all. And that is how you solve problems related to principle of inclusion and exclusion. So now let's have a more difficult problem where it pertains to three sets. So I will let you read this by pausing the video first for a while to absorb the problem, and then we can go from there. So after reading the problem, I have simplified the given items needed to solve for the main question: how many of these 2,504 students have not taken a course in any of the three programming languages? So from there, we will start by creating our Venn diagram. So we can say this one is Java, this one is Linux, and this one is C. Okay, so this is Java, C. Okay, so first we go from bottom up, from more specific to less specific. So first we have 189 students taking all three, so that would fall under here. Then we can actually go and choose one of the three to solve which one we want to find first. That would depend on you. So in this case, let's solve for those that took Java and C but not Linux. So that would fall under here, this area. So how do we look for that area? We subtract 189 from 290, which would lead you to 8. This is 1. No, that's not it. Yeah, 101 students over here. So these are the ones that took Java and C, but not Linux. And then we solve for the next one. So we're done with this and this. We solve for those that took Linux and C, but not Java. So again, subtract 189 from 231, which would result you to, this is 1, this one's 13, no, 2, this one's 7, 2, this one is, okay, that's not right. So again, 231 minus 189. 42 students, 1, 3, yep, 42 students. That took Linux and C, but not necessarily Java. And then lastly, for this part, those that took Java and Linux but not C would contain the following. Subtract 189 from 876. So minus 189 would result to 6, 7, 687. So we would have 687 students that took Java and Linux but not C. So then we can now proceed to the more specific cases, more general cases rather. So let's look first for those that took Java. Or let's do C first, because that is the first one here. So let's add first these three. As we will need it to compute for those that took C only. So that would be 12, 30, 332. So 345 minus 332 would be equal to simply 13 students. So we're done with this one. So now let's proceed to those that took Linux only. So in that case, that would be 687, 189 plus 42, which would result to 18, 16, 20, 21, 818. So 999 minus 818 would result to 181 students that took Linux only. And then from those that took only Java, we add 687, 189, 101 again, like how we did it in the other items. So 101, that would be equal to 18, 17, 978. Right? Yeah. No, it's not right. This is actually 16 plus 1 is 17. 17. And 9. Okay. So subtract 1876 from 977 to get those that took only Java. So that would be 16 minus 7 is 9. $899 students that took Java only. And then we take the grand total of the sum to get those that have not taken a course from any of the three programming languages. So that would be done by adding all of these numbers and subtracting it from 2,504. By doing the computation of adding everything, you should get 2,000 2,112 students that took either of the three languages. But since we're looking for those that have not taken either of the three, we subtract it from 2,112, which would result you to 392 students. So if we say that the universal set is the school, those students that have not taken any of the three would be placed outside the union of the three sets. So it would be outside um, the three sets, but it's still part of the universal set of computer science students at a school. So the answer would be 392 students. So now we will proceed to the exercise for principle of inclusion exclusion. So this one would contain two sets, and you will need to find out how many students are in the class, how many students chose one game and not the other, how many students did not choose a game, and how many students did not choose this specific game. And that's all for the discussion on sets.